gears just a little bit. Talk about something more, maybe more glamorous to you all than data cleaning. And talk about the point of why I spend so much time cleaning data. So everybody should be able to see screen. Anybody not able to see the screen?
We can't see that.
You cannot see the screen.
We can.
We can, okay. All right, because I can't see thumbs up if I put the screen up. Need a second monitor. All right, so as I've mentioned a few times, basically what I do, a lot of the work I do is we connect data across different state agency systems. And so a big part of that work is what's called deduplication, getting rid of redundant people, multiple records and systems. And why that's important, obviously you shouldn't have more than one birth record, but oftentimes agencies that provide programming want to know how many people do we serve? And you'll hear things like, well, we conducted programming with 35,000 participants last year. Yeah, it was 3,000 participants that you interacted with 10 times. So sometimes they really want to know, rather than how much are we programming, how many different people are we reaching with that programming? So this is where things like deduplication come in. People want to know what is the unique sample of touches, or what is the unique group of kids who overlap from being born in Iowa to ending up in kindergarten in Iowa. In order to do those sorts of things, and as part of trying to do those sorts of things, we also have to link data together. And so data linkage is quite an endeavor that hopefully will be enjoyable as we talk through it in the next 30 minutes or so. So deduplication, pretty straightforward, removing redundant records. We just did a little bit of it, pretty straightforward examples of deduplication. Ideally, we're focusing on two issues: whether there's exact redundancy, so we got rid of somebody who had exactly the same data across the entire record, or if there's partial redundancy. Sometimes partial redundancy is something we want to keep. So think about the first example when we got rid of a record because there was more information in the corresponding same ID. Deduplication is also important for data quality concerns, counting people, counting observations, overestimating the number of observations, underestimating variability if you have multiple cases who are in fact the same individuals. And chiefly in my work, duplicate cases make for a very, very noisy process in trying to connect data systems. So here's a quick example. This is a study that I was involved with a couple years ago with some colleagues. And everybody by this point has probably heard of Amazon Turk and no longer uses it to collect data, or maybe you do. It was all the rage for a while, and we actually just wanted to run a quick study to get some data to evaluate a measure. But we also were interested in what kind of data we would get from Turk workers. And so it was an online survey. We restricted participation to people who were 45 years or older. There was a short screener they had to get through that had some tricks in it to try and keep bots out and things like that. Then we also required that they have US stationed IP addresses. And so the nice thing of why we were trying to use mTurk is because I think in 5 days we got 10,000 hits on that survey, which is fantastic if you need a lot of data in a hurry for a little bit of money. Not that we intended to publish any of this data, it was more of a curiosity thing. But one of the initial things, data cleaning, that we had to start working on was what happened. So the first thing we did is counted duplicates, right? There's nothing necessarily stopping somebody from trying to access the same survey twice, although we wanted to prevent that from happening clearly. And so we looked for location markers. And in the particular application we were using, it would stamp with latitude and longitude estimates. Not that these are gold standard estimates. I think they're zip code precise, something along those lines in the particular application we were using. So we wanted to know, okay, latitude and longitude, how many times did we get hit from the same general geographic area? So that's what's running down the left column of this table, the number of hits from the same, exact same duplicated latitude and longitude. And so this is all the way to the finite second points. One hit from a particular area, 83 hits from another particular area, 114 from another particular area. All seems possible, right? Particularly if you're talking about a zip code precision, maybe even a block precision, city block. So the other piece then we want to look at is device hits. Software we were using also collected the IP address from whatever hit it. And so we see hits 1, 2, 10, 17, all from the same device. Weren't too concerned about 1 or 2 because a home computer, either a couple or roommates who are both over the age of 45, perfectly valid completers of the survey. And so what we were concerned about is then tracking those in sort of a multivariate or conditional or bivariate distribution way. How many hits did we get in the location from the same device? And then we were concerned about how many of them made it through our short screener or did not. And so we can see that when we got down into the 83 hits from the same location, 17 of those 83 came from the exact same IP address. Most of them didn't get through the screener, only 3 did. And when we got down to the 114, those all came from about 6 different IP addresses. So there were multiples. I didn't show them here, but there was one that was, I think, 54 of those came from a single IP. So that got us curious enough to dig further. We also got timestamp information, which I haven't shown here. The table got too big. But that timestamp information showed that of these 114 hits, about 102 of them occurred within 2 minutes of each other. So literally something was hitting the survey every 2 or 3 seconds from the same place on one of about 5 different devices connected to a different IP. And so then when we geo-located where this latitude and longitude was, it was in front of a courthouse in upstate New York. And it corresponded with these 83 that were in the middle of a lake in Kansas. So clearly an indicator that we had some redundancy. So we deduplicated those, took them out, and obviously didn't want them in the data. Luckily, most of them didn't get through anyway. So deduplication, we talked about yesterday, data structures, general data structures. Single record systems. You have one record and there is a unique ID for that record. Duplication, probably the result of an administrative error or an entry error. Somebody did something twice. There was a paperwork snag somewhere. It's pretty straightforward. You just deduplicate the file by the repeated IDs. So we did that with our previous data cleaning. Longitudinal record systems, this, again, remember from yesterday, is a situation where you have a single unique ID per person who has multiple records over time, usually. Here, duplication is a problem because it creates that overcounting, that noise. There really isn't 16 people in the file. There's an individual who went to school for 16 years. So there, again, we could deduplicate within the ID. Right? If we had this file in long format and each person has 10 rows, well, we just go through and take out one of those within the ID. Last major system, multiple record systems, it's where we have an individual who's tagged potentially with multiple IDs who also has multiple records under each of those IDs. Here we have an overcounting problem that's a little harder to get our hands on. We also have the issue of needing to preserve the ID keys. Right? If an individual has 4 different IDs that are linked to substantive data, we need to make sure that if we assign them a new ID, we can connect it to those 4 original IDs. And so here, deduplication is a little harder. We might have somebody with 6 different IDs. So we might deduplicate the data within an identifier set if we have one. So by ID, again, pretty straightforward. We have an original file. I showed you this file yesterday. And you notice that each person is in there potentially multiple times. Remember yesterday we created a new person identifier for them to make them unique from each other. If we decide then that we need to deduplicate this file, Alice is always person 1, Doug is always person 2, Edward is always person 6. So we can just reduce the redundancy and end up with a file of 6 rows reflecting each of these individuals. Now, note that each of these particular lines on the left could be tied to different substantive data. That's okay, because now we can always link Alice back to whatever original IDs may have been tied to those 3 rows. Okay, so we're preserving that ID key if there is one. Within ID deduplication then is a little bit different. And this is a case where we saw with our record of May Leilani in previous data cleaning work, where we have the same ID repeated over time, but the information in the records is not consistent. Okay, so in this particular example, we have an individual named John Smith who is male, who was born on January 10th of 2010. Oh, sorry, 2008. And none of those records in the top show that. Each one has a piece. And in fact, each one has a piece that is repeated a number of times. And so what we want to do, and this happens incredibly often when you have repeated records over time, they never get entered the same way. What we want to do is end up with a single line record that reflects John Smith. And so what we do is we deduplicate the file within ID using some sort of decision rule to maximize or collapse the information we have. And a particular decision rule that we take advantage of quite a bit is a majority rules decision, where if John, J-O-H-N, shows up more times than anything else, that's probably the record's real first name. Smith, again, showing up more than any other spelling is probably the correct spelling. Same thing with gender, birth year, month, day, and other information you might have. So when we deduplicate within ID, we end up with a single row for every ID with the most commonly occurring entry in that row. When there's ties, we have the option of pre-deciding whether we're going to take the first observation or the last observation. Again, that's usually tied to timing. Okay, so if Johnny, early on in his education career, becomes John, we might decide to keep the John if they're equally occurring over time. Okay. Deduplication within identifier sets works much the same way, except that the IDs are different, right? So we have people with different IDs where it's actually the same individual. And so they're color coded here. But what we're trying to do then is also get back to that same format of a single record per individual per ID. And so here we end up collapsing the yellow lines together as Jim Smith. We take the first ID here, which happens to be 300. Same thing with the blue lines. We collapse James Smith. We keep his first ID. The gray lines, you'll notice, do not get collapsed. And the reason why this happens is we're using an exact match on the entire string length, that right column that says name key. And those 2 gray records for ID 305 and 306 are not identical. Everything is identical except the gender. And so we're deduplicating within the full set of information we have. What is identical across the entire set? Can we reduce down to a single individual? Okay. So those multi-system identifiers, they're nice when we have them. They allow for direct matching across different systems. The most common multi-system identifier, meaning a single indicator or a single identifying piece of information across multiple data systems. The most common one being your social security number. Anybody know of any others? An identifier that is unique to a person that crosses different data streams. No, you do not have to duplicate each individual row by row. I'll show you a quick and easy way to do that shortly. Ideas for other identifiers that are unique to an individual that cross different data systems. There aren't very many, actually. Driver's license numbers, a good example, if you stay in the same state, although your driver's license in Iowa and Virginia or Oregon would be very different. Passport number, if everybody had one, but they do stay consistent. So if we had that information, we could definitely use it as a deterministic or consistent matcher across data sets. Yeah, it's unfortunate, I guess, that we don't have a number or something that works everywhere. But I also guess that if we did, I would probably be out of a job. So maybe that's okay that we don't have a lot of them. But when you do have them, so all of these examples, if we were trying to link people up across within a state, driver's licenses would be great. Passports across states, across countries. Social security numbers, when we can get them, they do link things, although it's not always the case that social security numbers are available. Birth records don't necessarily contain them, at least historically. Some states, they're not required to contain them. But when you have these identifiers, these sort of direct matching identifiers, matching is what's called deterministic. It's pretty easy. The ID number in one system has to match the ID number in the other system. So we did a little bit of this yesterday with school IDs, right? We did an inner join on these two files and got our exact matches out. Pretty straightforward, pretty easy to do when that information is available. Differential system identifiers complicate things, but direct matching sort of goes out the window at this point. Unfortunately, your social security number will not equal your student ID number. Your birth certificate number does not match your social security number. And if you have some sort of system specific ID, I don't know, like your university ID, that probably doesn't match anything. Particular programming IDs don't match anything. And these are what you're typically facing when you get data from multiple systems. You're going to be dealing with identifiers that don't have a linkage to each other or to anything outside the system itself. We might then go, okay, I have no ID numbers, but I still have information. I could employ a deterministic or exact matching process by identifier sets because someone's name is always their name. That's not true. I'm a classic example of this. I'm reminded quite often. My first name is legally William. I've never used it. So I show up in some data sets at state and federal levels as William Abraham, and most others as Todd. Good luck matching me together if I don't have an identifier. Even names that are consistent, common, what we would call derived or shortened versions of common names. So William, a nickname is usually Bill. Abigail, Abby. Those are not going to match each other across two systems. Birth dates are always birth dates. You've got those going for you. That's not true at all. They do not ever match. Birth dates give you 3 opportunities to make a mistake if you're entering them. You can make a mistake on the month, you can make a mistake on the day, you can make a mistake on the year. Worse, and you, I guarantee, have all had this experience, if somebody asks you, particularly like at a store checking out or someplace trying to go in, if somebody asks you your birth date, have you ever gotten it wrong? I get mine wrong all the time. I'm pretty good on the month and the day. The year gets me from time to time. So they're not always consistent, and they're not very distinct. There's only so many birth dates. Classic example of the birthday problem. So we're kind of in a situation here. What to do, and that's what we're going to talk about now. What do you do when you don't have an identifier? What do you do when you know that you're not going to get people exact matched by name, birth date, and so forth? We shift over to a sequence or a process an approach, a methodology, however you like to define it, of probabilistic matching. And what we're asking here is, how similar are two records across two data sets? We're asking the question here about how similar is the name in one file to the name in another file. So Jennifer and Jenny, reasonably close together. Lucas and Luke, reasonably close together. They're not identical. They're not exact matches. What about dates? 2011, April 7th. 2012, April 7th. 2011, April 17th. How close are those dates? Sorry, somebody have a question? Okay. So, in probabilistic terms then, we focus on two major probabilities. They're typically labeled M and U, arbitrarily. M is a probability related to the reliability or accuracy or quality of the data. Okay? So if I know that I have two data systems where I know that the names were entered without mistakes in both systems, there are no typos, everything is exactly the way it's supposed to be, the quality of that data or the accuracy of those name fields should be pretty high. That is, their M probability is high. So someone asked, do we need to see all of these similarities or code them? We're actually going to go through a process of record linking that does this for us. We still need our eyes, but it's not as intensive as you might initially assume, okay? So we will get there. In addition to M probabilities related to the accuracy of the data entry, okay, the data are entered poorly, the M probabilities are low. You have U probabilities. And U probabilities are commonality, uniqueness of the data. Something with very low commonality has a low U probability. Okay, so that means it happens all the time. If I'm dealing with a cohort of data where everybody's born in 2016, every birth date is in 2016, I have absolutely no uniqueness in year, which means it has no utility in terms of probabilistic matching anything. Everybody's going to match because they all have the same value. These two probabilities then are going to work together for us. So this is a very conceptual overview. The process itself is much more detailed, the theory behind it. Glad to talk to folks about that outside of this presentation if you're really interested. But as from a conceptual standpoint, we're taking those M and U probabilities in combination, and we're creating something called field weights, or column weights, if you want to call it that. And what those are doing is using the M and U probabilities in concert to differentially weight agreement and disagreement across two entries. Okay? So if I know the data are entered pristinely and there are no mistakes, I have this high M probability, versus if the data are really sloppy, a lot of mistakes, I have very low M probabilities. And so if I have that high accuracy, right, there are no mistakes in the entry of the data, then if two records don't agree with each other, right, there's no mistakes, then it's pretty likely that those two records are not from the same person. Make sense? However, the U probability becomes involved here because having a match between two records, there's no mistakes in the data entry, doesn't necessarily mean you have matched two records correctly. Gender is an example. I have two data sets where gender is entered perfectly accurately for every individual. If two people don't match on gender, they're probably not the same person with high likelihood. However, if they do match on gender, that doesn't really tell us much about whether they're the same person, because there's a 50-50 shot of matching on gender. The same thing would happen with birth years if we had a truncated cohort. So if we had 3 years of birth years, the odds of matching somebody are 33% randomly if everything's entered perfectly. Same thing with birth month. So this is where that U probability interacts with the M probability to determine the differentially valued mismatch or match across each record column, essentially. So some things to consider that get tied into this. How do you match text? Right? We have names typically that we want to match. How do you know the quality, the M probability of name entries, the uniqueness of name entries? There's a couple of things that are out there that are useful, more or less, dealing with text entries, particularly names, but they can be applied to other things like addresses or regular just text strings as well. That's how they were developed. One common one is something called SoundX, which is a phonetic coding system. There's a bunch of rules to it. There's an algorithm, right? You could go through and code text yourself. I wouldn't. Basically, the gist of the code, the basic idea, is that whatever the text string starts with is the first letter of the SoundX code, unless it's a vowel. Vowels are not coded. And then each subsequent letter or letter sets are assigned a different code. And so what you get is a code that is a letter and 3 digits. And that is supposed to be an approximate equator for things that are homophones, that sound alike. And so here are a couple of examples of real SoundX codes. You can see that the names are spelled a little bit different. Stephen with an E-N, A-N, and then Stefan. They all get the same SoundX code because they all sound alike. Okay, so S315. Likewise, Dylan, Dylan, and Dylan spelled 3 different ways, gets the same SoundX code. So this can help us rough match differential spellings, typographical errors, but it's not optimal. SoundX has some problems with non-character letters. So you see in that second row, Stefan with accentuated letters doesn't get coded. Same way that Dylan doesn't get coded. But we do get the same codes with some weird typographical errors like numbers inserted, punctuation inserted. So this is one way of matching text, but it's not terribly precise. And in fact, it can't be based on the algorithmic coding system. Below in the tables are actually a quick series of names I thought of one day that actually all yield the same SoundX code. Every one of those names, if we were relying solely on SoundX, would match each other. They would be considered the same person. And that's clearly not a threshold we're happy with. Some improvements and complements to things like SoundX are actually developed string similarity measures. One is Levenstein similarity. The idea behind this is it counts the insertions, deletions, substitutions that are necessary to change one string into the other. So if you think about the word the, T-H-E, and the word they, T-H-E-Y, there's one insertion that's required to make the, they, or one deletion required to make they, the. Same process. And so what the idea is that you assign an index score, essentially metricing how far apart 2 strings are. So the names Lydia and Linda, they receive a Levenstein distance or similarity of 0.6. Lydia and Linda a little bit farther apart, meaning that there's different transitions or transpositions that need to happen to make Lydia into Linda than Lydia into Linda based on those spellings. The metric is capped out at 1, which would indicate perfect match, 0 at not even close. Another common measure operates in a similar idea. It's a Jaro-Winkler distance. It's also a text similarity measure that indexes transpositions between strings, so typographical errors, letter flipping, those sorts of things. It tends to place a little bit more weight on the start of a string vector than Levenstein similarity will, which can be good if you assume that most people don't get the first letter or 2 or 3 of the name they're writing wrong. So here you can clearly see that there's a higher linkage between Lydia and Linda, or Lydia and Linda when Lydia is spelled with a Y. But note that these are not necessarily on the same metric. So a 0.89 on one is not comparable to a 0.89 on the other. That doesn't mean they're the same degree of match. They are both scaled so that they range between 0 and 1. And so the little plot over on the side is just a plot of distances on a series of names I generated. And you can see that they generally agree. Levenshtein similarity, if it's high, will be high in Jaro-Winkler's distance too. But there's a little bit more precision in the Jaro distance measure. So it tends to be the one that we rely on most for equating or probabilistically equating strengths. Some practical problems, the fun stuff. Compounded names. We've seen a few of these now in some of the example data sets we've been working with and examples I've shown. Hyphenated names, names with spaces, things like that. What do you do with them? And so if we look at the left side of this, say these are the original files we have that we want to link, and they're from 3 different systems. We might have the best quality data from the first system, okay, the most complete data. John Smith, Johnny Smith Jones with a hyphen, John hyphenated James Johnson Miller, John Paul Jackson Reese Avila, hyphenated and spaces. These might be the top quality or the most complete data we have. The likelihood of those individuals with multiple entries in their name fields showing up that way in every other data system they might appear in isn't very high. It's not uncommon for all of a sudden one part of a hyphenated name to show up in one data system, potentially the other part of a hyphenated name showing up in a third data system. And so when you're trying to compare text strings, you can see that just having multiple names can create a little bit of a problem. There's no way you're going to get a high Jaro-Winkler or Levenshtein match between Jackson Reese Avila and Avila. They're not going to be that close, even though one's contained in the other. So if you think logically about the number of transpositions or additions or deletions that would have to happen to get from Jackson Reese Avila to Avila, it's a lot. So what we typically want to do, and this is why we spent so much time in the cleaning work dealing with spaces and punctuation and suffixes and those sorts of things, is that we want to take our data systems and split those records. So anywhere that a name field contains multiple entries, Smith Jones, we want to turn that into 2 separate lines of data. We actually want to create a line of data for Johnny Smith and a line of data for Johnny Jones. Notice that their birth date remains the same because they're the same person. Their ID remains the same. And we want to do this with everybody that happens to have multiple names in the fields that we're working with. This can become a little long. I mentioned somebody with 9 middle names. Yes, they ended up with 56 lines of data. But what we're trying to do then is capitalize on John Paul Jackson Reese Avila showing up in some data system as Paul Reese. Okay? That's a match. It's just not a match you're going to catch with any direct deterministic comparison. And so if we do this to every file that we're going to attempt to link, obviously we're going to end up with repeated people. We might suppose Johnny Smith Jones is in all 3 of these files as Johnny Smith Jones. Well, then we're going to have a match between Johnny Smith and Johnny Jones, and Johnny Smith and Johnny Jones, and Johnny Smith and Johnny Jones, right? We would get 2 matches across each of the files. So we then are going to end up backtracking towards that deduplication process again, so that we don't end up with overcounting. But here, because they all have their same IDs, that deduplication becomes deterministic based on a single identifier. Other practical problems. I know this is not an ideal graph to be able to see, but just visualize a big picture here. Two things we fight with this is it's probabilistic, so there is a likelihood of false positives, matching the wrong people to the wrong people. We hope not to do that, but there is really no way you know if you've done it, other than hopefully they're close enough. So there's always this possibility of false positives. One thing that we can sort of hang our hats on is that what these are, these bars, these are two real data systems that I work with. And we went through and combined all of the demographic information we have into different combinations. So the one way up here at the top that's really small is first name, last name, gender, year of birth, month of birth, date of birth. And then way down here at the bottom is year of birth, month of birthday. So what these are, I started with both of these systems. So there's about 310,000 cases in one and about 150,000 cases in the other. We went through and deduplicated out anybody that was repeated based on both their IDs and their exact matches across the entire system. They're two systems that should be single identifier, meaning that you shouldn't have two student IDs or two birth records. And then we went through and tried to match up just how many times do you find people that have the same combinations, exact matches on these elements. And so what you'd expect is if we got rid of all the exact duplicates across the records, there are no randomly lucky matches on first, last, gender, year, month, and day. There shouldn't be. We got rid of all of them. So as we kind of go down this process of combinations, you see that the error rate, remember there's no real matches in these data, we're well under 5%, even if we're just using 3 elements out of the data, first name, last name, and birth year. We're still around 2% error. First name, last name, and day of birth is even more finite. Here, because the years are truncated, they're all young kids. So what becomes clear here is that there is error, but it reduces to the degree that elements in the demographic table match up. And it decreases pretty rapidly. Alternatively, you would never want to just use somebody's birth date as a matching mechanism, because you're guaranteed after about 50 cases to have somebody born on the first month and day, or on the same month and day. As your years get truncated into a cohort, that's going to go up exponentially higher. In addition to false positives, we have false negatives. And this is just the reverse, missing correct matches, not catching everybody that we should be catching. There's no way we're going to get everybody, but we do our darndest to try to. And this is where my current work falls right now, is in our system, we're doing a great job of matching cases. We've got some little problems to work out here and there about incorrect matching, but we've identified where it's happening. What we're more concerned about is who we're not catching and whether those misses are systematically biased. There's some evidence that we might be over or under matching based on a couple of elements. One common element is split last names. And so here are 2 examples where those folks, when they get split, can end up being perfectly matched, right? So if we cut their last name into 2 rows, we have a row Ana Hernandez in one data system and Ana Lopez in the other. They don't match. But we have Ana Garcia and Ana Garcia in the 2 systems. If those 2 cases happen to have the same birth date, they're different people, but we end up almost perfectly matching them, or perfectly matching them to the degree that we've weighted things that way. The same thing with David Von Diess and David Von Hackler. Clearly 2 different people, but if we split those names into multiple rows, David Von matches David Von perfectly. So we're trying to work out those systematic biases. Second place we have an issue that I'm currently doing some work on is order of operations. There's one way of solving that problem to involve a step where we don't just split names and attempt to match, we actually go through some sort of variant of the name matching process. Here, instead of retaining spaces, get rid of them. Actually truncate the entire strings down and then do the match from that perspective first. So it's an interesting set of problems. It's an interesting approach to linking data, but there are some complications. And it does have some system specificity, but it's fun work to think about. So any questions on the ideas or logic behind deduplication? What about record linkage? Everybody feel solid with it? Everybody's happy? We covered the logic, so I'll be referring back to a few things that we talked about on Thursday last week. But you won't need to go back and actually look all that stuff up. So if you want to work along and run code, go ahead and start up an RStudio session in Ravana. We'll be using the same repository. The GitHub repository has the information that you'll need and the data you need. As soon as I remember what I did with the link, I will post it in the chat if you need it again. We open things all at the same time. So here is the link to the repository. And there will be an R script file again that is called Data Linkage DSPG 2020. So that name is also there. And we'll be using two different data sets that are in there today. They are not exceptionally well named, but one is called Cleaned Unsplit DS, and the other one is called Cleaned Unsplit FRX. So they're both CSV files. If you wanted to grab them and work on your local machine, feel free to do that. Give everybody a minute to kind of get up and running here. Those files are, again, completely made up names. If you're interested in trying to find yourself in there, go ahead. I didn't purposely put anybody in there, but generating random names is an interesting endeavor. And so some of those names are things that we saw last week in the data sets we were using. Some are new folks who are completely made up. And even though the data are clean, they're not perfectly clean like we talked about last week, because I needed some inconsistency to show you how probabilistic record matching works. If everybody was perfectly cleaned up, there would be exact matches and we'd be done in about 5 minutes. So this will be a little bit more exciting and probabilistic. So I'm going to go ahead and switch over my screen to my R window. Has anybody had any trouble initializing and getting set up, ready to go, or is everybody good? I don't see any pop-ups in chat, so we'll go ahead and share this over. This should be my R window. All right, so my screen should be visible to folks. And you should have this R script open. We'll be loading two packages here. One is data table that we've used before, you've used for other things. The other one is a package called record linkage. You might need to actually install it. I had to install it a couple of weeks ago using Ravana, but it should work. It should work just fine. As a check, you could probably just run the library command and see if it loads, but if you do need to install it, let me know not to just fly on with the rest of the code. Has anybody been able to load that? Anybody having trouble? All right, everybody's ready to go? So, as we talked about last week, linking records across different systems is commonplace. It's interesting, and it allows you to answer some interesting questions for people in different agencies who would like to know stuff that other systems have that they don't. And we talked last week about that being relatively easy when there's something nice, like a social security number that doesn't change over time. Some good ideas came out about driver's license numbers, passport numbers, those sorts of things. Unfortunately, that's typically not the case. Usually each individual data system uses their own IDs, if they use any at all. So then we talked about all of the potential things that go wrong when you try to deterministically or exact match people on their names, their birth dates, all host of things like that. So these two files, the first one is just file 1, file 2. I went really vague in general here, but assume that these come from two different systems where there are some people in both of the files, but they don't have any obvious way to connect them. So the first file I call DS just because it's data system. FRX, I don't know what that stands for, I just made it up. So feel free to call FRX whatever you like. But if we load these two files, you should see that one of them, file 1, is pretty large relative to file 2. So we have about 12,000 people in the first file, about 4,000 people in the other file. Clearly there's not going to be a one-to-one match of cases here. The files are not terribly large. They're only about 7 variables each. And that's connected with what we did with cleaning last week, where I separated out name fields, separated out birth date elements. Gender is another variable that's useful here. Those are my typical go-tos. Most systems collect that information. Obviously, there's potential systems that collect additional information. If so, that can be included in this type of matching too. The files that we just loaded are both typical data files. Each person, each ID has a single row as a record. And if we just take a quick look at one, we view it and scroll around a little bit, you'll notice that some people are missing. Some people, like I said, these are not perfectly cleaned. Otherwise, this would be a pretty quick endeavor. There are some split names. So actually up here, we have separations between parts of names that occurs both in the first and last name fields throughout. And we talked last week about a way of capitalizing on that, where somebody might have 2 official first names, but use one or the other in different systems. The same thing with things like hyphenated or combined last names. Sometimes those get slammed together in particular systems. So Scotty Jackson, that might have been a hyphenated name in another system, might have been split by a space in another system. And so last week when we talked about these sorts of things in record linkage, we talked about splitting those. So if somebody does have multiple entries in those fields, what we actually want to do is create multiple rows in the data for them to maximize the likelihood of combining them across 2 different systems. So the next part of the code here, Aaron, creator, actually wrote these original functions for us in Iowa a couple of years ago. It's a set of functions. One is a pretty simplistic string to vector function. The other one calls that in the new rope or string item function. And if we run those two together, you run both of them. You don't have to run them necessarily together. This gets at, there was a question last week about all these possible combinations and we have to code each of these different things and break them all apart manually. This function does that for us. This is actually going to take any spaces in a name field and break that information into a new row. And so what would happen if somebody has 2 first names, 1 last name, a birth date, and gender in this case, they'll now have 2 rows where the only difference between those rows are their first names. They'll still have the same ID number that they had, same last name, same birth date, and so forth. So each of these new lines of code here perform that step on each file. You can run them both together. This takes a couple seconds. Obviously, this is a labor-intensive computational issue, so you can run them both together. And it'll be a second. It doesn't take a full minute for this to happen, but if you're using RStudio, you'll notice there's a little red stop sign down there in the console that's telling you it's working on this problem. And what this is going to do is produce two new data sets that we will refer to here as prepared, where there will be extra rows. We're not adding new people, and so we finished one. Here goes the other. But we'll have these two new data sets, and these are actually the data sets we'll perform the matching on. So we have these at multiple rows per person. So the second one is done. Yours hopefully are also finished. You can take a look at these now. Just take a look at anybody who has an ID number that repeats. The initial files, the first file 1 no split and file 2 no split, nobody was duplicated in those. And so if we click these head commands, we now see that we have folks who initially had a single line of data. So here's a particular case, just grabbing one randomly, where it was, the initial entry was Sarah Louise Rutherford with this birth date, 8/20/1988. That individual now has two lines of data separating out those names. And the reason we're doing this again is so that in case in the other system that person appears only as Sarah or only as Louise, we capture them. That does raise the possibility that they appear the exact same way in the other system, file 2, and that they now have two lines of data in that system. So we will be looking at eventually deduplicating the files once we're finished with the match. And so these two files, there's file 2, we see the same sort of thing where people are repeated, okay, are now ready to go through the matching process. One thing I like to do at this point is to actually deduplicate these files. And the only time this occurs is if somebody actually has the same name twice in the same field. So John Smith, there will be a line in for John Smith and another line for John Smith. That complicates the process. It's noise in the system. So it's just an exact deduplication on the full row of data. If there's an exact copy, I like to get them out of the way. And so we could actually look and see if that happens here. And we do. We have 17 lines of data in that first file of now 13,000 lines that are exactly the same with another line. So we'll get rid of those 17. They don't add any information for us. We check the same thing with the second file. Did anybody get exactly duplicated there? We have 9, so we'll get rid of them. Just to clean out redundant information. We're not getting rid of any of those split lines that differ in any way, it's just the ones that were split that are exactly the same. And so now we're ready to embark on the matching process, and so there's some aesthetic things that are nice and handy here. We're creating a couple of abbreviations that we're going to be using to tack on to things later. Also some ID numbers that we'll be using to tack onto later. So all these 4 lines of code are doing here are just setting some things that we'll be passing to our processes later. It's just a quick efficiency step. And so when we do that, we'll just create some elements for abbreviations and IDs that will affix to things later. Realize that what we're going to end up with now at the end of this is a file that has an ID for the DS system and an ID for the FRX system. We want to make sure that all of the information in those two systems is clearly labeled, identified. So now this is actually our first step in the linkage process. And this is what the record linkage package does for us. It is designed to probabilistically compare 2 data sets and identify and connect matches. It can also be used to deduplicate files probabilistically, and it can actually perform a deterministic match. It's relatively straightforward to do here. What we're doing is we're entering those 2 data sets, the ones that we've now split rows into. And so we have multiple rows for people who had multiple names. And remember last week I showed you a chart or a graph that was showing you error rates, people who match exactly on first and last name and birth year, even though the files shouldn't contain any matches, sort of those false positive things. Now, someone had a question about having to enumerate all of those. You don't, but they're handy pieces of information. That third line here that says block field, block FLD, this is an optional step, but it's a useful one. If we did not have this step in, what the code would do here, the compare linkage package would do here, the command would do, is generate all possible pairs of individuals across these two data sets. And so we have just over 13,000 observations in one, just over 5,500 observations in the other one. That's a lot of pairs of people. This would take quite a bit of time, quite a bit of processing time, and it really wouldn't be all that helpful. We don't want to end up matching anybody that doesn't have any element in common with somebody else in the data systems. So these block fields, these are not arbitrarily chosen, but we're going to say that folks should be retained if they match at least on last name, first name, and birth year, or if they have a match in the other file on last name, birth year, and birth month, or if they have a match in the other file, first name, birth month, and birthday. Again, these are not arbitrary, and if you go back to the slides we looked at on Thursday of last week, you'll see that there's different error rates associated with these. If we were conducting an exact match, we could just say block field is last name, first name, birth year, birth month, birthday, and gender, and put all 7 variables in there. What we would get back is all of the exact matches across the 2 files. Alternatively, we could put in more or less restrictive blocks. So if you think back to the best situation in the example I showed last week was very few errors when you match on first name, last name, birth month, birthday, birth year. In fact, you shouldn't get any errors if there are no duplicates or matches in the system. Alternatively, if we were to block field by just birth month, birthday, and birth year, that wouldn't be very helpful because, as you guys learned with Heike, either yesterday or Friday, the probability of having the same birth date with somebody is pretty high once you get around 50 or 60 people. Okay? So that's where these block fields come from. An important point about this, though, is that whatever you put there will eliminate people. So if there's a case in one file that doesn't at least match on last name, first name, and birth year with a case in the other file, they're eliminated unless they match the last name, birth year, and birth month of somebody in the other file. If they don't, they're eliminated unless they match the first name, birth month, and birthday of somebody in the other file. So anybody that doesn't have at least a match on those pieces of information is removed. The exclude command is just something to indicate that you don't want to be matching here on IDs. If I had other information in the data sets that I know don't match, I would put those in this exclude column or command as well. The next line down, string comparison. We talked last week about a couple of different metrics or similarity indices for comparing string text. We're going to be using the Jaro-Winkler similarity that we talked about last week here to probabilistically equate or identify similarity between the 2 name fields across the 2 files. And so that string comparison command that just says 2-3 is indicating which columns those text fields are in. In these files, first name is the 2nd column, last name is the 3rd column. And the comparison function is that Jaro-Winkler. So we're set to go ahead and run this, except that we haven't assigned those M probabilities that we talked about. Remember, that's the accuracy of the data. We might be pretty confident. We might know that first name, last name are very well collected, very well entered. We might know that birthday is very error prone. Sometimes these can be directly estimated from the data. Other times you trust one data system more than the other. So in my case, we usually default to something like a birth records file that the birth date's probably right in that one. So we might put more weight on birth dates if we're using that file as one of our matches. These are just weights for those columns though. So first name, last name, gender, birth year, birth month, birthday. If we upweight, make those weights higher, then we're putting more emphasis on a match on first name. Or if we make them lower, less emphasis on whether or not gender matches across file. So much so that we could remove any one of these and we would put it up here in the exclude command. So I have a system that we use quite a bit where they failed to collect gender for about 90% of the sample. If we're matching that file to another file or that system to another system, we really don't use it. It doesn't do us any good. These are changeable and it will result in the different set of matches potentially. It's all a function of how much you're weighting equality or similarity on each of these fields across the two files. So once we've applied those, we're ready to run this. And so if we run the pairs compare linkage command, it runs and we get this large record linkage data set. It actually contains a bunch of things, so we need to work through pieces of it. Right now, it's just created pairs of everybody. We now want to assign these probabilities to those fields. And then the next command, we're asking it to give us out the weights. Okay, so we talked about field weights last week and then a cumulative total weight across these, in this case, 6 pieces of matching information. Key piece of information here is we're assigning to those pairs that have been made now, those M probabilities that we just assigned. And then we're also setting a cutoff value of 0.9 here. That's related to that Jaro-Winkler distance. So we're not requiring an exact match on first name. We're requiring a match that's close within a Jaro-Winkler distance of 0.9. So I showed you a few examples last week. A typo will still have a high Jaro-Winkler distance, but it's not optimal. There are some cases, common nicknames that don't have a very high similarity measure. So what we're trying to catch here are things like typos, transpositions, things of that nature. So if we assign those, okay, we now want to go ahead and take a look at what weights we have, what cumulative match weights we've computed here based on the pairs that we assigned and identified in the data. So this table command will kick out all of our weights. These weights are not in a metric that's directly comparable to things. They're basically just scaled numerically as a function of what we used up here for M probabilities, this cutoff value, which if the Jaro-Winkler similarity between a first name in system 1 and system 2 is above 0.9, it's called a match. If it's below 0.9, it's not a match. And then also the U probabilities. Remember we talked about uniqueness in the data. So these numbers will change down here, these weights. They'll change from application to application, but the ranking is what's important. So the highest weight in this case is a 44.24 roughly. There are 822 pairs that have that weight. It's usually the case that those are your exact matches, people that match exactly similarly on name, birth date, whatever elements you're using across the two systems. And then we see walk back from that. So these might be the folks who differ only on an element we downweighted, maybe birthday. These folks might differ in a pair only on 2 elements, or the similarity between their first names in the two systems is further apart. All the way back to maybe these folks. These folks down here would be pairs that don't match very closely on much of anything other than what we specified up here in these blocks. So they at least had to match on these. Does everybody still have audio? This happened to me yesterday during Heike's presentation. Everybody else was still good except me. Okay, so, all right, some folks did. Yeah, that happened to me on Heike's. All of a sudden she's just talking. So, okay. So here now we have a decision to make in terms of the quality of these matches. And usually the best way to do that is to actually just look at what is different, what is not exactly matching. So here we're going to extract out a data set from this large pairs file. And we're going to set the weight. Here, I just want to look at this group, my 44s. So I'm setting the minimum weight at 44, max at 45. It's only going to draw out these pairs. And so if I do that, I can now look at a data set of just those matched pairs. And so what you'll see here is that there's a new ID assigned. This is within the matching. Here are their original IDs. So this person appeared as Matisse Arc in the DS system and also as Matisse Arc in the FRX system. Female in both systems, same birth year in both systems, same birth month, same birthday. So these are exact matches. That's why the weight is so high. All of these cases then are likely exact matches across all of the elements except their IDs. Okay, so we definitely would consider those matches across system. Next, I'm going to go down and look at a different band of cases. How different are these? Because remember, we're doing this probabilistically, so these are probably pretty close, differing maybe only on one thing, a typographical error in gender. Maybe only the birth date is off by a day or two. Maybe their names are just slightly misspelled in one file or the other. So we typically go through a series of this. Here I'm going to look at everybody who's got a weight down in the 30 range. So these folks. I'm going to do the same thing. I'm going to extract them out as another data set. Take a look at that one. And we see same name show up. But notice here, so keep in mind that people can get matched multiple times. There'll be, like I said, there will be a deduplication step. But we can see what differs here. It's just the first name. In one system, Matisse showed up with the full name. In another system, only partial name, but the birth dates are still the same. See the same thing here. And if we were scroll down a little bit, we'll see that there are differences that are due largely to a slightly different first name. I'm going to do this again just one time to look at the people who are down a little bit further. So now down in the 23 range. These folks down here. Extract them out. See how they differ. Okay, so here, this first case that shows up with the weight down in 23, the names are exact matches. Gender differs. Birth year is exact. Birth month and birthday differ, but they don't really differ. This is why cleaning data is so important. Standardization of data is so important in this process because these are essentially an exact match that only differ in the gender column, but because there's a 0, 2 here and a 2 there, that's not a match. And so those folks are getting pushed in as essentially poor quality matches only because of a data cleaning problem, but there are some other issues here too. So like in this case with Tanner, same name, missing gender in one system, same year. This is clearly a typo. So we should have caught that during the data cleaning process too. Essentially, if we kept doing this and checking every one of these bands, we'd get down to something that we consider unacceptable. They only match by first name, birth year, and birthday. So Sarah was born on April 10th and matches Sarah, who was born on April 10th, but they're 5 years apart in birth year. And so this is a decision that you make walking through these bands. Once you've decided what you're going to call your cut point, you then split out everybody who's above that. So this match command now, I'm going to keep everybody, all the pairs that have a weight higher than 23. And this is what I'm going to consider my matched file. So if I run that, you can now see that the file is aligned across the two systems with their weight in there. It's potentially an easier comparison to go across if you want to go across rather than up and down. But we now have everybody that we think were close enough in terms of their matching. So now we have some cleanup stuff to do. What we're going to do now is create a new file that just has their IDs from both systems and that weight variable. And then I'm going to just rename those very quickly as file 1 ID, file ID2, and WT for weight. So this will be a small file, these 3 lines of code. And it's just those 2 IDs, what their ID was in the DS system and what it was in the FRX system and their match weight. Those match weights will obviously then range from our high of 44 to just above 23 that we used for our cutoff. And remember that people can be in there multiple times. They can be matched to multiple individuals. They can be matched repeatedly within the files. So now what we're going to do is go through and remove duplication. And we're going to do this in a very simple way, but essentially we're going to sort the file by their ID in one system and deduplicate so that only the ID tagged with the highest match weight is retained. And then we're going to sort by the other ID and do the same thing. So what we should end up with is a final set of cases that are the closest matched in one system to the second system, or the closest match in the second system to the first system. Okay. So if we run here, we'll notice that our match IDs will shrink a little bit. So we go down from 2659 to 1836. Those were duplicated cases that are kicked out. Now we do the same thing for the second file. We sort by those IDs and weights. And so we'll lose a few more cases. We lose about another 35 to end up with a matched file of approximately 1,800 cases. Now what we have, if we actually went and looked at this, is just those 2 IDs and their weight. We want to put their original data back together with them. So that's what we're going to be doing this next near final step. We're going to take this weight file and reattach or merge or join, we talked about that last week, the original data sets that we read in, the non-split ones. So we're going to bring those first in for the first system, match their information back. We can take a look at that. Okay, so now this is the matched weight here, their ID in both systems, and then these are the original data and how they appeared in that first file we started with. And we'll do the same thing for the second file. We're going to now bring those data in and merge that to this file. So we matched by ID in the DS system here. Now we're going to match to ID in the FRX system here. So now we have our individuals here in the first system, their matched line in the second system. And we're just going to clean up the column names so that they don't have .x and .y in them. Just going to go ahead and polish those up. Get rid of all of that stuff we don't want. Remember the abbreviations we created earlier, the DS and FRX abbreviations. We passed them here so that now we have their ID in the FRX system, the ID that they had in the DS system, their first name, last name, gender, birth year, birth month, birth day in the DS system, and the same information in the FRX system. And so what we'll be able to see here, if you scroll through and look, you will find, and particularly if you walk by weights, right? So here's our 23. We can now compare. Robert Lang, gender was different, 2007, February 20th. Birth dates are different, okay? The quality of the matches is then something you would investigate rigorously at this point, and in the extraction part where we're looking at different weights. In this case, we're satisfied that most of it's typos and poor cleaning for the lower weights. We now want to check and make sure that we don't still have duplicated cases in there. And so where this will happen is if you actually have somebody that has the same name, same birth date, or very similar to another individual, they'll get matched twice. It's happened. There's really not a great way to deal with that if it happens. And it can also happen due to split names. That happens quite a bit too, where Smith Jones might be matched to Smith in the other file, and Jones might match to another person in the other file, in the first file with the name of Jones. So we check In this case, I don't have any of those
Allow.
by the first system ID. Somebody have a question? I heard somebody. Okay. And then I'm going to check by the second ID too, to make sure that I haven't matched the same individual to two different people. In this case, I haven't. If it does happen, I usually go in and do some investigating manually. It doesn't happen very often. And in some cases, there's nothing you can do. There's just two people that are a perfect match for one individual in the other system. Okay. So at this point, what we have is an inner joined file. And you could write this if you want to. I'm not going to save mine, but you could certainly save it out. This would be the file you were interested in if you only wanted the cases that were exactly matched between the DS system and the FRX system. Alternatively, if you wanted to put everybody back together, the ones that weren't matched from the DS system and the ones that weren't matched from the FRX system, we would perform a full join, which is here, and we'll walk through this in a minute. Where you would do this is if you wanted to look at representativeness of the people you did match across systems, did they differ systematically from the people you didn't match across systems? That's not always the case, but if it does happen, you want to go back and reconsider your matching process, particularly if you're missing a lot of people from one system that are in a subgroup that don't show up in the other system. Are you missing, are males failing to be matched more so than females? People of certain age groups, are they failing to be matched more than people of other age groups, and so forth, things of that nature. The other place this is really important to do in the work we do is that typically now that we've got this nice inner joined file of matches, I'll be coming back in with a third data system and I want to match those folks too. And I may be interested in obviously the three-way join, but I want to know if I have people in my DS system that aren't in my FRX system that also show up in my Q system. So I want to bring everybody back into the same file. And in order to do that, we have to redimension the original files. This matched file that we've created now has 15 variables in it. The original files had 7. So all of this block of code here is just going to go ahead and bring in that original file, kick out everybody that did not end up in our merged file, and then we're going to create some new columns and reorder some stuff. If you really want to walk through bit by bit and see what all of this does, feel free to do so. But I'll just show you what happens at the end. So we're going to end up with a new file that has extra columns in it that don't contain any information. So this would be our DS file. We still have a blank column for the ID FRX. That's what the middle 3 lines of code did. I moved that around. Their original DS ID, their original DS information, and then just blank columns. We're essentially squaring this data frame up to match the one we created that contains the merge cases. So we're going to do this again for the FRX system in a second file, which is the same block of code here, except we'll just be moving all the blanks to the front of that file. So we'll click that. Now we see the reverse. Their FRX ID is there. Their ID in the DS system is blank because they weren't matched. They have 7 blank columns for their information in that file. This is their original information in the FRX system. Now we have these 3 files. We just want to stack them together. And this is where somebody mentioned that set seed wasn't working the last time we were all together for them, that they were getting different results. I mentioned last week that our bind list, you should say usenames equals true because it matches by location. That happens in my office because I'm using a slightly older version of R. When I did this on my personal computer last week, using usenames equals true was throwing a warning. And if I took that off, it actually required specifying I want to say don't use the column names, use the locations. And so what we have here are the original merge file that has these 15 variables, and we basically created empty space for the people that are in the DS file that don't match somebody in the FRX and vice versa, people who are in the FRX that didn't match anybody in the DS. So now I really just want R to perform what I would say the least intelligent form of a row bind, and just put column 1 with column 1 with column 1, and column 7 with 7 and 7. So all we're going to do is just stack those up. Take a look at that. So now we have this stack where the first 1,800 or so cases will have data in both systems. Those are our matches. Those are the folks that we probabilistically linked. If we go down a ways, we'll have all of the folks that were in the first system that did not match anybody in the second system, so they have blank information. And if we go all the way down near the bottom, we'll have the reverse. Everybody that was in the second system that had no match in the first. And as I mentioned, this is potentially a file you would use to do some representative checking, looking for biases, looking for stuff that you might adjust in your cleaning process that is sliding through without matching. Or this is where you potentially would start to match in a third system or fourth system. And then the last bit of this, of course, is just to write out our final file. This is a simple one-time run through. Obviously, there's more to it than this in terms of adjusting those M probabilities. There's some preliminary work to decide on those. I showed you some examples of what happens when you alter the cutoff for the Jaro-Winkler similarity, where we might set that down lower in a second round of matching to try and catch common different ways of the same names, or short names or nicknames is one of the things we're working on now, where you have known nicknames like Abigail showing up as Abby in another system. The Jaro-Winkler distance might be very low, below our cutoff, so they're counted as a non-match. So this is an iterative process that we go back through quite a few times to try and catch as many people as we can, but then also trying to be very careful and being investigative of the final file to make sure that we're not linking up people who shouldn't be linked up to somebody who's clearly not a match to them. Any questions on record linkage, probabilistic linkage? A lot of fun. Mysteries abound. Okay, so if that made sense to everybody, I'm going to stop sharing this screen.